Welcome to this battery solutions or solutions for battery testing webinar presented by HIOKI Europe together with our UK sales partner, MDL Technologies. We are one of the manufacturers represented by MDL in the United Kingdom. MDL, of course, offers a lot of other solutions around what we do around battery testing as well. So this is not strictly battery testing sales partner, but of course also has other solutions in the test and measurement world. We are jointly doing this together. I think we have a couple of other guests here as well in this webinar, so welcome to everyone. And what we're going to do today, we're going to have a very, very brief history about HIOKI and lithium-ion batteries. That's really going to be a very brief history. And then I would like to take you on a little tour through a battery production line. But we're, of course, not only going to look at lithium-ion battery production, but we'll also look at R&D and quality assurance topics on top of that as well. So let's start with the very brief history of HIOKI and lithium-ion batteries. Just very quickly about HIOKI. HIOKI is a test and measurement company that started in 1935. The first product already was a test and measurement instrument, in this case, an electrical indicating meter. Today, HIOKI has about 1,000 employees, turns around about 200 million euros in as turnover. HIOKI is stock listed on the HIOKI Stock Exchange, but it is a very engineer-driven company. So the engineers really dominate the decision-making in terms of how to put the products into the market, and also engineering quality design is like product design, electronic product design is really an absolute core competence of HIOKI. One very important thing as well is our products are made in Japan. HIOKI has a factory in Ueda in the Nagano province of Japan, which is also the place where HIOKI is located with the headquarters. HIOKI has a European subsidiary actually only since 2017. So if you think, oh, I've never heard of HIOKI before, that may well be because even though HIOKI has started to make test and measurement equipment in 1935, HIOKI actually only established a European subsidiary in 2017. If you want to read more about that, we will share the slides later after this webinar together with the video link, I believe, but we'll definitely share the slides. And you'll see a lot of links in this slide set, starting basically with a little interview of our managing directors of HIOKI Europe. I'm not going to talk about that at all here. I'm just, if you're interested in knowing more about that, you can click on the link and actually find out how it's possible that HIOKI is in Europe with a European subsidiary only since 2017, when we've been making test and measurement since 1935. The product portfolio of HIOKI is a very wide one. It's not only focusing on battery testers or battery testing solutions, although battery testing solutions definitely is one of the core competences of HIOKI. HIOKI is making flying probe testers, in-circuit testers for automatic test equipment. We're making professional measurement instrument, and we're making field measuring instruments. So a very, very wide portfolio. Everything you can see grayed out or grayed backgrounded in this slide, battery testers, resistance meters, impedance analyzers, and so on. These are the products we're going to talk about or touch today. Again, all of these product types are links. If you want to find out more, feel free to visit our brand new website that has only been launched actually last week. So let's look at lithium-ion batteries, and you can see that the history of lithium-ion batteries really started in Japan. And this is not a slide that's designed to be death by PowerPoint for you. This is really only the most important thing on this slide is the circled 1985 on the slide. And that's really where lithium-ion batteries started in Japan, when Asahi Kasei, or a fellow of Asahi Kasei, produced the world's first production viable lithium-ion battery. And actually, if you look at the concept of that lithium-ion battery, that's very close to the lithium-ion batteries that we're still using today. So 1985 really is the only information that is relevant for this, what I'm trying to point out here, for this on this slide. Because on the next slide, you can see when did HIOKI actually start to make battery testers, and that was in 1986. So if you wonder, wow, 1985, the first commercially producible lithium-ion battery came on the market. 1986, HIOKI already made the first battery tester. How's that possible? If you want to find out more, again, click on the link in the slide. But basically the point I'm trying to make here is HIOKI has a huge amount of experience in the area of battery testing and battery test solutions, of course, not only limited to battery testers. And that actually is the reason why, while we're talking about battery test solutions in this webinar, we're actually going to spend some time focusing on other products around battery testing, because the battery testing at the end of the day happens at a very late stage in a battery production process. And as I said at the beginning, I'm going to take you on a little tour through a lithium-ion battery production line. And this is, if you look at the setup of a lithium-ion lithium-ion battery manufacturing process, this is kind of like how it starts with slurry at the very beginning over electrode sheets. Slurry goes on electrode sheets. You've got tap welding, vacuum drying, discharge aging, cell testing, and modules and pack testing. So we're going to touch a couple of these parts. We're probably not going to look at all of them. We're very likely not going to look at all of them. We're going to start actually not with the slurry, but we're going to start with the electrode sheets. And if you look at a battery electrode, or if you look at a lithium-ion battery, then it's basically there's three major substances, and these substances are the electrode, the electrolyte, and there is a separator. And if you start to look at the electrode, then you can see that there is a composite layer, the active material, and then there is an interface between the composite and the current collector, and then of course you have the current collector. Now, lithium-ion batteries tend to be used in high power applications. Just think about a car. Don't even have to think about a racing car. Just think about a normal car. That is a typical high power application. So it is absolutely crucial that you have a low composite resistivity on one side in the composite layer, but also that you have a low interface resistance between the composite layer and the current collector. The big challenge of that is, of course, how do you quantify the resistivity of the composite layer and the interface resistance? How do you get separate measurement values, which is something that is actually really important also in the R&D part of a lithium-ion battery, because the better you can do this, the better electrodes you can create. Of course, the more efficient batteries you will have at the end. So there are traditional ways to evaluate electrode sheets, and that, of course, is the penetration resistance, which is a 4-wire measurement that you would do. Same thing as a 4-point probe method. The difficulty with that is it is very, very difficult to quantify what is the interface resistance and what is the resistivity of the composite material, because you will get one value but not multiple values. You will not get separate values for the composite resistivity and the interface resistance. And also the big challenge is, of course, with this type of measurement, it is very difficult to get repeatable data. It is possible to do, but it is very, very difficult. And what is definitely not possible is you cannot get different results for interface resistance and composite resistivity. But there is the solution, and the solution is coming from HIOKI. It is called RM2610, and this is also a nice showcase of what HIOKI is actually able to do in terms of test and measurement. If you look on the right side of the slide, you can see in the bottom, on the top picture, you can see the probe head of this resistance meter RM2610. You can see that on the top side, you can see the bottom of the probe, which would be lowered onto an electrode sheet. On the bottom, you can actually see the probe, and the coin or next on the left of this probes of this little probe, next to it is a coin, and that coin is a 1 euro cent coin. A 1 euro cent coin has 13 millimeters in diameter, and next to that, you can see this bundle of little pins, and the size of this total bundle of little pins is only 1 square millimeter, and there's, I think, 46 pins on the space of 1 square millimeter. And this probe set, or this probe tip, these multiple probe tips allow you to actually make multiple measurements and then take these measurements, put them into a 3-dimensional mathematical model, do a calculation. And the outcome of that is the value for the interface resistance and the value for the composite resistivity. So it is possible to actually get separate values for that. You actually only need 3 informations that you need to feed into the system. One is a composite layer thickness, the current collector thickness, and the current collector conductivity. And that is all information that is easy to obtain when you're in the process of developing these kind of products. I'm not going to go too much into the details of this measurement principle, because if we would, then we would basically spend the rest of this webinar just focusing on the measurement principle of this system alone. So again, if you want to have a little bit of a deep dive into this measurement principle, then there is a link into a technical paper which really elaborates very, very detailed on how the measurement principle has been realized. For me, this is a very, very interesting product over here in Europe, because it is really something that can increase, not in the R&D part, it can really increase the time to market. If you want to develop new battery cells, this one allows you to increase the time to market. I would love to show you a list of customers for this product. Unfortunately, of course, we're not able to do so. All these kind of sheets, they say confidential, but there is an internal slide which basically just has the logos of all the Asian customers of this system, and it's really the who is who in automotive, and it's the who is who in battery manufacturing is on that. Actually, this product sold to 50 companies before it was actually launched. So there was a prototype development stage of the RM2610 before it was launched in July 2019 for about 3 years. So for about 3 years, there was still the final development going on. And in this time, already 50 companies have purchased altogether more than 80 of these units, because there is nothing else like that on the market. And it really allows you not only to reduce your R&D time by allowing you to actually not finishing to make the battery and then see whether the electrode was good, but you can very, very early on make predictive measurements that allow you to say this battery is going to be good because the electrode is going to be good. So not only in R&D, this is a critical instrument, but also in manufacturing, because when you have an electrode sheet manufacturing process, you've got all kind of different variables that you can change. That can be anything from a press pressure of the material, it can be the drying temperature or anything like that. If you make any sort of changes within your manufacturing process, the RM2610 does allow you to actually monitor the effect on the electrode sheet and allows you to make sure that the quality remains the same. And of course, finally, quality inspection and control, especially when you buy electrode sheets from a third party, this instrument allows you to make quality checks for incoming third-party products, as well, incoming third-party supplier material as well of electrode sheets. We're actually making a little jump now, because coater press, slitting, and sheet cutting and stacking is not really anything where too much electrical measurement is going on. HIOKI is an electric measurement company, so we are jumping basically to the next point about in the lithium-ion battery manufacturing process, which is electric, and that's the tab welding part. Sorry to say, we're talking about another resistance meter. We're not at the battery testers yet. We're talking about another resistance meter. Why is it important? If you have a high resistance in a weld connection that can heat up your cell, And we all know the last thing you want is heat in your lithium-ion cell. First of all, it can damage the cell, but also it is an additional resistance because you want to get that energy out of the cell for your application, and you don't want to burn that energy to heat up a poor connection. Typically, the aim is to keep the contact resistance of these kind of tab welds below 0.1 milliohm. Typically, from everything I know, the majority of customers do test these weld connections all the time. So with every cell, this is a test that is conducted. I know that I actually know of only one customer who's doing weld testing and prototyping and then doesn't want to do that later in the production stage. We do recommend to do these kind of weld tests with every cell that you do, with every weld contact that you do, because it's such a critical thing to keep this contact resistance of welds at the lowest possible point. And this is a very, very early way of quality assurance and making sure that the overall battery pack at the very end doesn't have lose one of the weak points within that system. So it's very, very easy to filter out bad welds and cells with bad welds very, very early. So what is the method of that? It is just a very, very traditional 4-wire measurement method. It's a DC measurement method, and it's simply goes over the tab welds, goes over the contacts, make that and test them in micro-ohms resolution, test the weld quality. The interesting thing about the product that we're talking about when it comes to that is a resistance meter called RM3545. The interesting part about that, it is actually already made to be integrated into a productive or production environment. You can see that because there is a model which allows you to add multiplexer units into that, which means you don't have only one tab weld measurement that you're going to do, but you can actually do that multiple times. And then you have a multiplexer unit and you can just switch through these. So you basically make one physical connection with multiple test pins, and then you just switch through each test point, make the measurement. This happens in less than 2 milliseconds. And this unit has multiplexers included. The important part is if you're planning to make use the multiplexer units, which are actually an option, when you get the RM3545, you need to make sure that you have that version that can hold the multiplexer units, because the standard version does not hold multiplexer units. It doesn't have the kind of like places where to put these multiplexer cards. You can put the multiplexer cards in later at any time. But you really want to make sure if you use this in production that you already purchased or bought the unit that already allows you to add these multiplexer units at a later stage, because that is a really, really fast and very, very good way of making a lot of tab weld measurements at the same time. You don't need 100 of these units just to do that, but you just need one, and you have several multiplexer cards, 2 multiplexer cards, which means basically up to 20 channels at the same time. We're moving on a little bit. We're moving on before we're filling the electrolyte. And sorry, again, we're not looking at battery testers yet. What we're looking at is insulation testing first, because this is typically done before electrolyte is filled. We're dealing with high voltages or high test voltages. It is not something you want to do after the electrolyte has been filled, for the simple reason is you don't want to damage the cell. So the proper installation is absolutely crucial, absolutely critical. It not only protects against the degradation of the battery life, but it also protects against accidental fires, because you know that what can happen if a lithium-ion cell starts to burn, starts to have a short cut somehow, and that can have quite heavy effects. Everybody remembers the cells in I think it was a mobile phone from Samsung, which started to catch fire in aeroplanes. One of the things in that case, I'm not sure if that was an insulation problem, but you could see the effects that a lithium-ion cell can have once it catches fire. Insulation, proper insulation is absolutely crucial to ensure that that doesn't happen. And one of the instruments that you can use in production line to make sure that that doesn't happen is the ST5520 insulation tester. Another option is the SM7120 insulation tester. The most common one is the ST5520. It's the smaller one. Why do I even point out the bigger one? That has several reasons. One reason is very rarely the insulation voltage or the test voltage of the ST5520, that's only 1000 volts. And there are some customers who say 1000 volts isn't enough. And they would then be able to use the SM7120, which allows to go up to 2000 volts for that as a testing voltage. I know of one customer in Europe where 2000 volts isn't enough. They're actually using a cell test voltage, or for the cell installation, they're using a test voltage of 4 kilovolt, but that really is the exception. The vast majority of people using the are using the ST5520 with a voltage typically around 500 to 1000 volts as a test voltage. The big difference between the ST5520 and SM7120 or 7110, if you use the smaller model, which also only goes to 1000 volts, is you can set the test voltage with a resolution of 1 volt with the ST5520, and you can set that with 0.1 volts with the SM7120. Why is it important to set test voltages at 0.1 volts when you're actually looking at test voltages between 500 and 1000 volts? Actually, for that, it isn't. But you can also use the SM7120 or 7110 at a later stage, which is make some tests after the electrolyte has been filled. And in that case, you will use a much lower test voltage. And in that case, it is actually interesting to change the test voltage in the 0.1 volt resolution and not only in 1 volt resolution. But typically the most common insulation tester you find very, very widely is the ST5520. And now actually what we're going to do, we're going to look at what happens after the electrolyte filling has happened. And now you see the little brother of the SM7120. Now it's the SM7110. Again, if you want to find out about the products in detail, there's a link in the slides. I'm not going to go too much into the details about the products. So what you can do is you can now do resistance measurements and basically insulation tests by setting the nominal voltage of the cell, which would be something like 3.7 volts. And in that case, just having what the ST5520 would allow you to do, have 1, 2, 3, 4, 5 volts, it wouldn't be precise enough. So the SM7110 allows you to set the voltage to like 3.7 volts because of the resolution of 0.1 volts. And then another thing in insulation testing is a precision DC voltmeter. And you might wonder, why on earth are they using insulation? Are they using a precision DC voltmeter, basically one part of a multimeter? Why are they using that for insulation testing? And this is something that allows you, the digital voltmeter allows you to measure a couple of scenarios simply by checking what is the actual voltage measured between certain contact points. And you have different types of failure modes, which is between positive negative electrode and package aluminium, negative electrode and package aluminium, and between the electrode and the package aluminium. These are the typical failure possibilities that you can actually find with a DVM. And these would be the test results that you would find if you would find these effects with a DVM. One of the crucial things with that is, though, that you need a contact check function, because what you need to be sure is when you make these measurements, I'm just going to jump back. When you make these measurements, you've got to be sure that you actually have a contact between for example, at the very top picture between the positive and the negative electrode. If you have no contact, a normal digital multimeter would show you 0 volts, because no contact in a multimeter is always 0 volts. The difference with that and our DVM would be that there is a contact check function, which is a capacitive contact check function. And that actually figures out, do you actually have a contact to the DUT? And if you don't have a contact to the DUT, the display or the message will show there is no contact. And that, of course, is the crucial element. That's why you cannot use any digital multimeter that you have sitting around to make these kind of tests. That's the reason why you need a measurement instrument with a contact check function for this. We actually created a very, very crude YouTube video. I keep saying this is not going to win me an Oscar for best light and sound. It was actually made on this desk on an evening of a turnaround of a demo. But that actually is going to highlight, or that will highlight, if you click on that link, you can see very, very quickly what's the difference between the DMM and what's the difference between this digital voltmeter with a capacitive contact check function. And you immediately know why it's important. We're moving on again. We're moving towards discharge aging. Discharge aging is probably not something you are going to do when you're producing 18650 cells. At least you're not going to do that outside of A sample, B sample, C sample, like outside of the prototype phase in standard production, because that is simply not something economically viable to do. However, there is an awful lot of special purpose cells, high capacity cells, cells made for example, racing cars, which now have electric or hybrid systems inside of them. And for these kind of high performance cells, actually making an aging or go through an aging does help to figure out whether your production process is good and whether the cell is going to have the durability that you expect it to have. All of this is basically based on an OCB measurement, and it allows you to detect, for example, metal contamination, collector cuttings, which are still remaining somewhere in the battery. You have some active layer powder from the cutting of the electrode that remains somewhere. You've got burrs on the side of the collector. These are the things you can detect with aging. And really what you basically do is you take the battery, you make a measurement at the beginning, you make a measurement at the end, and you see how much self-discharge has happened in that time. And from that, you can see if you've got a good cell, the self-discharge will be very, very small. If you have a higher, if you have a high discharge, that is going to be, of course, it basically indicates that you have some issues in the material of that cell. Again, something you very, very often use in the prototype part, but not necessarily only, but it is, of course, something when you set up your production system, this is a very, very good way at the very early stage to figure out, do you have things which you need to optimize in that process. Cell testing, we're actually starting to move towards battery testers. We have said that this is a battery testing solution, and so now for about 30 minutes, we haven't mentioned battery testers, apart from saying that they will come at a later stage. So why is cell testing important? I mean, this is almost kind of like a bit of a no-brainer. You need to find out the internal resistance values, which is an important indicator for battery characteristics. And at the end of the day, this is one of the most crucial parts that you have at the end once your cell is finished. The important part about that is there is different types of cell testing or pack testing. You can have, first of all, DCIR measurements, you can have ACIR measurements, you can have multiple frequencies, which then is electroimpedance spectroscopy, and you have the classic ACIR measurement with a fixed frequency, which is typically 1 kilohertz. So we're going to have a look at these. First, the important part is the DCIR versus the ACIR measurement method. The DCIR measurement is the classic measurement method that you can do, but that basically means you need to charge your battery or your battery pack or your battery module, and then run a discharge. And during the discharge, you measure the internal DC resistance. The downside with this system, of course, is it takes quite a long time, because first you need to charge, and then actually you have the discharge process as well. And it does require preliminary charging, which means you need some sort of a power supply and an electronics. You need a power supply and an electronic load for the charge and discharge process available. Now, you can see that from this slide, HIOKI says the DCIR measurement has issues, while the ACIR measurement has advantages. And that, of course, suggests that the ACIR measurement is the superior one, because it has a much faster test time and there is no preliminary charging required. But of course, we have to say that there are situations where DCIR measurement makes sense, and where DCIR measurement is important as well in a battery production process. Because at the end of the day, this is the way to do the actual test if your battery is okay, because you can finally see, is there anything getting warm or not? You have checked everything in advance, check the tap welds, make sure that nothing gets warm. You have probably done EIS at the time, you have done ACIR measurements, but the actual real live load test is only something you can achieve with a DCIR measurement, which is crucial when you are dealing with big battery packs, for example. At the end of the day, the way we write it is HIOKI does not provide solutions for the DCIR measurement, but our partners typically always do. HIOKI sells through sales partners, and HIOKI is always typically one solutions provider for one type of technology. In this case, for battery testing, we have a very wide portfolio where we have solutions. But the DCIR measurement is one where your partner can help you probably with another manufacturer. The ACIR measurement, on the other side, it is also something that is absolutely crucial to do. There is even a standard that highlights that you have to make ACIR measurements at 1 kilohertz. So this is not something that you can just skip. And also the nice thing about the ACIR ACIR measurement is it is an extremely fast measurement, especially when it comes to cell and final inspection of packs. But what happens, it's a 4-wire measurement, and you have an AC current that is injected into the battery. At 1 kilohertz, this AC current does not have any impact, neither when it comes to charge or discharge, because that frequency is kind of like too fast to have any impact in terms of charge discharge to the battery. So that's one of the reasons why 1 kilohertz is the very safe one, and has been established over the years as being the kind of standard one. But also you have to look at what kind of information do you read at 1 kilohertz, but we're going to have a look at that in a second. So if you look at the impedance or the circuit model of a lithium-ion battery, then you can see that there is kind of 3 frequency spectrums that you can where you can get information from a lithium-ion battery. One is the lithium-ion diffusion, that's the so-called Warburg element. You find information about that below 1 hertz. Then you've got the lithium-ion charge transfer reactions, which are between 1 hertz and actually a few hundred hertz. And then you have it's called lithium-ion migration in electrolyte. That's the electrolyte quality that you can measure at around 1 kilohertz. And that is the reason why the battery testers with a fixed frequency are also at 1 kilohertz, because it allows you to check whether the electrolyte is okay. If you look at this on the little graph on the left of this slide, you can see what is called a coal plot, or basically a Nyquist plot. And you can kind of see the reactance over the resistance on this. And then you can basically see we're doing a frequency sweep. This is basically electroimpedance spectroscopy, which means you do a frequency sweep. Typically with lithium-ion batteries, it's 0.1 hertz and then going up to about 1 kilohertz. Within that range is where you can find interesting information about the cell. Important part, this is just looking at cells. So we're talking about the lithium-ion battery. A battery can be just one cell. Just think about the 18650. It's one cell, but at the same time, it's a battery. But the point of the whole thing is that at this moment, we are looking on cell level, 3.7 volts. That's typically where you do electroimpedance spectroscopy. And what you can see is electrolyte resistance. The information about that is what you get at around 1 kilohertz. And then you get the charge transfer resistance below and diffusion resistance. Forget about the diffusion resistance. I think at this moment, there's not too much information that you can get out of that information in battery production. And now we basically put the picture just at the moment, a second ago, was the principle, the principle of this kind of Cole-Cole or Nyquist plot. This now what you see is a real life, proper measurement between a new lithium-ion battery and a degraded lithium-ion battery. And you can basically see that the R1 would be the 1 kilohertz measurement that you do. And you can actually see that the difference between R1 of a degraded lithium-ion cell and a new lithium-ion cell is very, very small. So it's very, very difficult to make a prediction of the state of health of a battery if you're just looking at 1 kilohertz. But at the end of the day, if you're in battery production, that's not an issue at all, because in battery production, you know that your cell is going to be new. And at the time when you actually test the cell, you already have done insulation tests, you've checked your electrode, you've checked that your electrodes are fine. So basically, what are you checking on cell level is that, did the electrolyte filling work properly? Is there enough electrolyte in it? Because, for example, if you would have, if the R1 would be too high, for example, that it would show that there is a too high concentration of the electrolyte, which means something has gone wrong during the filling process, for example. Why would you probably use EIS in production, like EIS as in electrochemical impedance spectroscopy? Why would it make sense? Because it is, of course, a time-consuming process. If you measure every cell and you go through every cell with a frequency sweep, it does take some seconds. It probably, even if you do multiple measurement points in a very low range, it will go probably even into a minute of testing time. Especially if you go at 0.1 hertz in that area, just look at the tau length. It's basically 0.1 hertz means 1 tau is at least 10 seconds. So the least amount of measurement time that you kind of have is 10 seconds if you want to measure 1 tau. So that's time-consuming thing. Why would you want to do it in production? And you do it in production if you want to do cell grading. That is very, very important if you want to create high performance pack. Think about race cars. If you think about these guys driving around in these racing cars at 300 kilometers an hour, then you know that every second can count. Every second can make the difference between win or lose. And if you can tweak, if you can optimize, tune your battery pack to be 99.9% good and not only 99.8% good by making a selection of bringing the right cells together, then that can make the difference between win or no win. So high performance batteries would be a typical example. Another example that we know is lorries, for example, lorry cells that you put into heavy electric vehicles, not the classic, just the people car, like a normal, I don't know, Tesla or whatever you would take, but think about a truck running on EV. The cells that you have inside of that are large capacity packs, and you want to make sure that they work well together in these huge setups. So there, in that case, it might also make sense to use electroimpedance spectroscopy. We have one customer in Europe who's making exploration cars. These cars go to deserts, go to the Antarctic, like real exploration cars, and the entire mains power comes from lithium-ion batteries. And they, of course, also buy these cells from a third party, and they actually test every single cell with this EIS just to make sure that they got the right cells, and just to make sure when they put them together in the pack that the pack performs as well as possible. So grading is one of the reasons. And of course, if you are buying cells from a third party, you also want to do quality checks before you assemble these cells to modules or packs. So from that point of view, EIS does make sense, but of course it doesn't make sense if you have a production line of 18650 cells. You're never going to measure 18650 cells and do an EIS sweep over it, because also you have to do something with the measurement data at the end of the day. And or alternatively, you do it just a bin, but that really doesn't make any sense. And why would you grade cell? Imagine you have one dot inside of it, one weak one inside of it. It would get heated up more than the others. It would probably deteriorate more than the others. And at the end of the day, if you have one battery, one cell in a series of cells that make a pack, at the end of the day, that one is the weak point that has an effect on the entire pack life. So that is the reason. But again, it is typically something you do for high performance. Then we have impedance analyzers, and the impedance analyzer for a battery would be the typical instrument that you would use when you make the grading, when you make an EIS. And we have two different types of these kind of analyzers. One is the more classic one designed for lithium-ion batteries. That's the BT4560. It would typically be remote controlled with a computer, and you would basically do the remote, the sweep controlled by the computer, while at the same time the IM3590, which is a chemical impedance analyzer, would be would even allow you to make these kind of Nyquist plots on the screen. You can use the IM3590 as well, of course, integrated into production environment. Typically, it's a product that you more find in the research and development part, especially if you look at the frequency range, which is between 1 millihertz and 200 kilohertz. Make a 1 millihertz measurement. Look at the tau time. That is 1,000 seconds. In a production line, you're not going to make a 1 millihertz test, at least not typically. There might be situations where it makes sense, but the amount of where these situations happen is very, very small. The important thing is, if you're looking at doing EIS, especially with lithium-ion batteries or lithium-ion cells, in this case, please be aware the impedance range of the BT4560 is much, much lower. So when it comes to high capacity cells, the BT4560 is definitely the more suitable instrument. When it comes to, for example, button cell applications, the smallest range, 1 milliohm of the BT4560 might not be enough. Your impedances might be higher. In that case, for button cells, for small capacity cells, the IM3590 is the most suitable instrument. And again, the important part is the voltage for these units is typically 5 volts. 5 volt basically means cell level. There are, from the BT4560, there are special versions available. HIOKI is making special versions of their products, and the 4560 is probably the product that has the most amount of special versions. That can mean that either the frequency is higher, there is a 10 kilohertz version, for example, of the BT4560 as well, but then of course the majority of customers, they just would like to have a 10 volt or a 20 volt battery voltage range. In that case, one of the things you've got to keep in mind is, if you measure, for example, 10 volts, if you need a 10 volts or 20 volts measurement range, you can be pretty sure that there will be series of cells involved. If you have series of cells, keep in mind that there is a battery management system, and you do also measure the battery management system with it as well. So you've got to be very, very aware of what you're actually measuring there, because the battery management system, of course, has an impact on your measurement as well. Now, finally, we're looking at the standard battery tester with a single frequency. And that is probably the most common thing that you think of when you think of battery testing. The most famous, most common one that you will find from HIOKI, and actually it is almost an industry standard, or it's de facto industry standard, is the BT3562. It has been revamped fairly recently at the beginning of 2021 to be a BT3562A. The only difference is that the voltage is a little bit higher than before. The maximum voltage is 100 volts. The previous model only had 60 volts. And the difference is that there is a network, a LAN card or LAN connection inside of it as a standard, which is just required in today's kind of environments. But basically, it's the BT3562 as from a measurement principle. 1 kilohertz is the important frequency. Again, why 1 kilohertz? It is a fast measurement, and not only the lower the frequency, the longer the measurement time, but also it doesn't charge or discharge the battery at this frequency. And of course, very important, 1 kilohertz is the standard in battery test production, or in the test battery production line. There is an IEC standard for that. So basically, you're kind of required in a battery test, in a battery production line, to do a 1 kilohertz test of your battery before you finish it off. But again, that's the important part. You actually only check the electrolyte and the connection resistance. But as I said before, everything else at this point has been checked in different kind of stages of the battery production test process. So the nice thing about the BT3562, it is a very, very fast measurement. It measures within 10 milliseconds. It's ideal also for large, low resistance cell testing because it has a 3 milliohm range. It has 7 resistance ranges, and also the voltage range of the BT3562, that is 6 volts, 60 volts, 100 volts. There are big brothers of the BT3562, and that's when we move more into pack testing. So far, this would be the tester that we would use for cells. But when we're looking at modules or packs, then there is a variety of different kind of bigger brothers and even smaller brothers of the BT3562. I'm not going to go through the details, but you can basically see that we can provide you with a solution to also test packs with up to 1000 volts. But I'm not going to go into the details. If you're interested into those, just click on the links in the presentation or just go on our website. Finally, we have this product again, which is the RM3545. We had it, you remember, tab welding, and I was telling you about the possibility to also put in multiplexer cards. This is of course not only good for tab welding, but this is also very good for testing the bus bars. If you're putting modules together, if you're putting cells together, you do that with the bus bars. Again, you want to have a smallest possible connection resistance. So this product comes in here at the same as well. Again, there is a YouTube video from HIOKI, which you can find out more about this. But basically, it's just the same type of measurement as with the tab welds. It's a bus bar measurement in that case. OCV measurement is something you do find when you do a DCIR measurement. So DCIR measurement, as we said before, it requires a power supply and electronic load. Of course, your power supply and your electronic load will know very well at what kind of current has been given and taken towards the cell, like for the charge and discharge process. On the other side, one of the things you do need is a very precise voltmeter. So a lot of people are using a standard DMM from one of the large manufacturers. HIOKI has a DVM, which is just a voltmeter, ideal for these kind of open circuit voltage measurements in the DCIR process. The nice thing about this one is it's not 6.5 digits as the standard DMM is, but it is 7.5 digits as a resolution. And the nice thing about it, it has a very, very high temperature stability. And finally, again, it has a capacitive contact check function, because when you do this in an automized way, one of the things you want to make sure that you have a proper contact to your battery pack that you're testing or to your battery cell that you're testing. And for that, the DM7275 provides the perfect solution with this integrated contact check function. Contact check function is actually something you see in a lot of instruments from HIOKI. I didn't mention it for the BT4560 or the BT3562, but of course, all these instruments have this kind of contact check function. The simple reason is they're designed to be used in a production environment. They're designed to be integrated into your automatic test environments. And of course, in that case, you need to be sure that there is a contact. Otherwise, the measurement doesn't make any sense. And our products do have this contact check function. Again, here's the link to that video with a DM7275 or 7276, just to highlight what is the difference between a multimeter when you connect to a cell and our DVM with the contact check function. Almost finally, you can, if you don't want to use, or if you don't have the multiplexer units within the RM3545 resistance meter, which we talked about, there are of course also other instruments which simply don't allow you to add multiplexer cards into it. For example, the standard battery testers, the DM7276, or also the BT4560. In that case, you still have the possibility to use multiplexer units because there is a mainframe and extension cards from HIOKI, which is called SW1002, and with the extension cards as well. You can basically find more details about this as well. Huge amount of channels you can add into that, so you can actually make a lot of like one mechanical connections and then do a lot of measurements at the same time. The kind of limit with this one, I'm just going back, the kind of limit with this one is 60 volts as the maximum voltage and 1 kilohertz as the maximum frequency. The good thing about this is you can absolutely easily integrate it into your LabVIEW environment. And I'm not going to talk more about this one. So pack installation with standing test. At the very end, you also want to do an installation test. And for this, we have the 3153, goes up to 5 kilovolts. And as I said before, there is one customer in Europe that actually uses this instrument for cell testing, but it is really rare that this happens. Typically, this instrument would be used as the final installation or withstanding test at the end of the production process. So maintenance measurements and lips, I have one slide, but basically it is only something, I'm not going to talk too much about it just from a time point of view. There is a link to an article about this. We had a look at this a little bit because there's a lot of people who, you can see that a lot of UPS batteries there's a trend of replacing lead acid by lithium-ion batteries. And we're just trying to point out that you've got to look out when you do maintenance measurements with a typical battery tester, which operates on 1 kilohertz, because as you've heard before, 1 kilohertz, it only allows you to say something about the electrolyte, and the electrolyte in a lithium-ion cell doesn't necessarily tell you too much about the state of health of the cell. That's it from me. I don't know if there are any questions or if I just completely flooded you with information now. I have no idea if there are any questions, Jensafik.
Yes, we have actually 2 questions coming up. One is from Mika. The question is, could I use the HIOKI instruments to evaluate the cell life in reliability testing?
To evaluate the cell life
in reliability testing.
Well, the cell life is typically something that the question is the cell life at the beginning of the process, or is it a maintenance measurement? If it's a maintenance measurement, yes, you can do that with the cells by doing an electroimpedance spectroscopy. It would require the BT4560 to do that because you need to look at a larger frequency spectrum and not just at 1 kilohertz. That would not be enough. So if you do on cell level, that's possible. On pack level, that's going to be challenging. But at the end of the day, state of health measurement is one of the most trickiest thing in lithium-ion batteries. There is not a very one-size-fits-all kind of solution. It is a very, very tricky topic. There's still a lot of research going on, I also know, within HIOKI to find easy solutions for that, because easy is the problem here. If that didn't answer your question, please also feel free to get in touch with me. My contact details are in this slide set as well, but you can also contact a sales partner or just connect me on LinkedIn or something like that. No problem. Just get in touch. If that didn't answer your question. Oliver, next.
We have, yes, 2 more. One, the question is, could you elaborate a bit more on RM3545, specifically resistance measurement for bus bar?
elaborate more. It's a DC measurement that we're doing. That's the important bit. On the bus bars, what you don't want to do this with an AC IR measurement. So you don't want to use a battery tester for this. The simple reason is you will create noise for that. You will have noise. You will have measure that will influence your measurements. So these kind of bus bar measurements are typically DC measurements. Not sure if this answers your questions, but it's actually a very, very straightforward measurement, because it's the same thing with tap welding. You want to have these connectors to be at a minimum, the resistances of these connectors to be at an absolute minimum. You don't want them to heat up. You don't want them to basically be a resistance for your current flow. So from that point of view, this is an absolutely vital test as well. Any kind of contact measurements is a really vital test. In production, you would do that with a RM3545. In maintenance outside, you would do it with a handheld version of the RM3545, which is called RM3548. It's a standard resistance meter, has the size of a battery tester, does a DC measurement, a DC resistance measurement, but absolutely crucial to check that contacts that you have, battery contacts that you have, and these kind of busbar contacts, that they are as low resistance, that they have a low resistance as much as possible. Again, if that didn't answer your question, please do get in touch.
Yes. Okay, then we have one more question, which may be a good summary. Also, do I damage the cell insulation if I perform repetitive IR tests on the same module? Is a question from Marco Padovani.
Do you damage that? Depends on the voltage. It completely depends on the voltage. If you're putting, I mean, again, has the electrolyte been filled at this point, or is the electrolyte still out? That's one of the questions. But of course, we are really advising not to use too much voltage, not a too high test voltage when you make these insulation tests. But then sometimes, because of the material of your cell, it might be required that you're using higher voltages, higher test voltages. Of course, you don't want to repeat them too many times, because every kind of high voltage that you put on material is going to have, at least has the risk of causing some sort of damage to your cell. So from that point of view, you don't want to do that repeatedly. But if you have an application for that, again, just get in touch and we can talk details, no problem.
Yes, all right. That summarizes all the questions we have in writing. So other than that, I think we would be happy if you get in touch for more questions or more explanations about this topic. Mm-hmm. Right?
Yeah, absolutely. Absolutely. It's definitely a super, super interesting topic at the moment, because wherever you look at the moment, everybody's ramping up in Europe this kind of technology. There is, every day you turn on the news, you basically have a new, oh, here's a gigafactory, here's a joint venture between a car manufacturer and a battery maker. A lot of the technology is based in Japan or in Asia. And what's really the nice thing, I mean, HIOKI is not a hugely known company in Europe, but at the end of the day, in Japan, we are really a household name. And Asia they are a couple of years ahead when it comes to lithium-ion batteries and lithium-ion technology. They are a couple of years ahead, and HIOKI has been there from the beginning. So from that point of view, we do have a huge amount of experience in-house. If we can't answer questions over here, we have direct access to the engineers in Japan, so we can always elaborate with them as well to find out more.
All right, good. Well, thanks again, Kai. Thanks to everybody for joining this 1 hour about battery testing solutions from HIOKI. And yes, we are waiting for contacts to get in touch to talk more about batteries or different topics about HIOKI. Thanks a lot. Thank you very much.
Enjoy the football tonight.
Thanks a lot. Goodbye.
Thanks a lot. Thank you very much. Bye-bye.